Have you ever just stopped and wondered what everything is really made of? I mean, the chair you're sitting on, the air you're breathing, even your own body. It turns out all the amazing, complex stuff we see is built from just a few unbelievably tiny fundamental parts. So today, we're going to decode the simple rules that govern those building blocks and, well, the entire universe.
All right, so here's our game plan. First, we'll tackle the big one. What is everything actually made of? Then we're going to shrink ourselves down and take a trip inside the atom to meet the particles living there. After that, we'll figure out how each atom gets its own unique ID, we'll meet some strange atomic lookalikes, and finally, we'll see how atoms get charged up, which is what makes all of chemistry happen. So yeah, let's kick off with that huge question. If you could zoom in, and I mean way in, past what even the most powerful microscopes can see, what would you find? What are the basic fundamental Lego bricks that build our entire world?
Well, it turns out those Lego bricks have a name. We call them elements. They are the purest, most basic ingredients you can find anywhere in the cosmos.
Think of elements like the primary colors of the universe. You can mix red and blue to get purple, but you can't break red down into anything simpler. It's the same with an element like pure gold or oxygen. You can't break it down with chemistry. And the absolute smallest piece of an element you can possibly have, that's one single atom.
Okay, so if the atom is the smallest piece of an element, the next logical question is, what's inside of it? It's time to crack one open and meet the tiny subatomic particles that call it home.
Right at the very heart of the atom, we find this thing called the nucleus. And you have to understand, it is incredibly small, but it's also unbelievably dense. Here's a crazy way to think about it. If an atom were the size of a giant football stadium, the nucleus would be like a single marble sitting on the 50-yard line, but that tiny marble would contain almost all of the stadium's mass. So this table introduces our three key players. Inside that nucleus, we have protons, which have a positive charge, and we have neutrons, which have, well, no charge. They're neutral. Notice their relative masses, 1. They're the heavyweights. But then you've got the electrons, and they're zipping around outside the nucleus with a negative charge. And look at their mass. It's so tiny, it's practically zero in comparison. This is a really important idea. The protons and neutrons give the atom its weight, while the electrons are all about energy and charge.
And that brings us to a super crucial point. In any normal, stable atom, the number of positive protons is perfectly balanced by the number of negative electrons. The +1 charges and the -1 charges completely cancel each other out, giving the atom a totally neutral zero charge. It's in a perfect state of balance.
So wait a minute. If all atoms are made from the same three particles, how do we tell them apart? How do we know if we're looking at an atom of gold versus an atom of, say, oxygen? Well, it all comes down to two really simple numbers.
First up, we have the atomic number, and this is simple. It's just the number of protons in the nucleus. That's it. But this number is everything. It's the atom's absolute unchangeable identity card. If an atom has exactly 6 protons, it is carbon, always. If it has 79 protons, it is gold, period. The number of protons defines what the element is.
The second number is the mass number. This just tells us the total weight of the atom's core. You just add up the number of protons and the number of neutrons. That's it. We don't even bother counting the electrons, right? Because, like we saw, they're so incredibly lightweight, they don't really add anything to the total mass.
Okay, let's put this into practice with sodium. So, you see here its mass number is 23, and its atomic number is 11. Right away, that atomic number tells us it has 11 protons. And since the neutral atom is balanced, we also know it must have 11 electrons. Easy. Now to find the neutrons, we just do some simple math. We take the total mass, 23, and we subtract the 11 protons. What's left? 12. So it has 12 neutrons. See? Simple.
So, we've established that the number of protons is set in stone. It defines the element. But what happens if we keep the protons the same, but we mess with the number of neutrons? This is where we get to meet some of the atom's strange doppelgangers. These are called isotopes, and they're basically just different versions of the exact same element. Because they have the same number of protons, they're chemically identical. They behave the same way. But because they have a different number of neutrons, they have different masses. It's the same element, just, a heavier or lighter version. Hydrogen is the perfect example to show this. Check out the 3 versions here. They all have 1 proton. That's what makes them hydrogen. But the most common version, sometimes called protium, has 0 neutrons. Then there's a heavier version, deuterium, with 1 neutron. And the heaviest one, tritium, has 2.
They are all hydrogen, but they just weigh different amounts. That's the whole idea behind an isotope.
Okay, so far we've been talking about these perfectly balanced neutral atoms. But honestly, that's where things are kind of quiet. Things get really exciting when that balance gets broken. This is how atoms get charged, and it's how all of chemistry really gets started.
When an atom is no longer neutral, we give it a new name. It's called an ion. And this only happens when it either gains or loses electrons. Remember, the protons are locked away safely in the nucleus. They never change. But those little lightweight electrons on the outside, they can be given away or even stolen by other atoms. And that imbalance is what creates an electrical charge.
Let's go back to our old friend, sodium. A neutral sodium atom starts out perfectly balanced, 11 positive protons and 11 negative electrons. But what if it loses one of those electrons? Well, now it's left with 11 positive charges, but only 10 negative ones. The positives now outnumber the negatives, so the atom has a net positive charge of +1. It has become a positive ion. Now let's look at the complete opposite. A neutral chlorine atom has 17 protons and 17 electrons, but it's kind of greedy. It really wants to grab one more electron. If it steals one, maybe from that sodium atom, it now has 17 positive protons, but 18 negative electrons. The negatives have taken over. This gives it a net negative charge of -1. It becomes a negative ion. And there you have it, protons, neutrons, electrons, and the simple, elegant rules that decide what an element is, how much it weighs, and what its charge is. Which kind of leaves us with one last massive question to chew on. If the building blocks are this simple and the rules are this clear, how do they possibly combine to create the breathtaking, messy, and infinite complexity of the entire universe?